Welcome, general chemistry students. Today we are working on chemistry tales and tale number 16, electrochemistry. Track 1 is going to involve redox reactions and electrodes. Okay, so electrochemistry is basically the study of redox reactions and the apparatus that are used to make measurements of electrical potential that happens when redox reactions occur. So let's get to some basic definitions and understandings of redox reactions. So what is a redox reaction? Okay, it's a reaction that involves an exchange of electrons. Okay, something's going to give up an electron or more, one or more, and the other substance is going to take those electrons. So it's important that we remember the tendency of different elements to gain or lose electrons. Okay, the property of electronegativity in the periodic table, if you will recall, electronegativity is the ability of an element to take electrons or attract electrons to itself. Okay, so if we go up a family in the periodic table, electronegativity is going to increase. If we move across a row in the periodic table, electronegativity is going to increase. So that leaves us with the most electronegative elements up here in the upper right-hand corner. So like nitrogen, oxygen, fluorine, those are the most electronegative elements. And elements on the left side, remember these are your metals. Okay, so your metals are going to have a tendency to give up electrons. Your more electronegative elements are going to have a greater tendency to take electrons. And so that's going to form the basis of most redox reactions. Alrighty, so some terminology that's important when we do redox reactions. Okay, first of all, what is a redox reaction? Well, an overall redox reaction we think of as the sum of two half reactions. The half reaction where something is losing electrons is oxidation, and the half reaction where the other substance is gaining electrons is the reduction. And so the overall reaction is the redox reaction. Okay, so let's look at the two half reactions, starting with oxidation. Okay, there's a lot of terminology when we do redox chemistry, so you just kind of be on your toes. Okay, what is an oxidation? This is the process where a substance is losing one or more electrons. And how we know something is losing one or more electrons, we have to go in and assign an oxidation number. And the substance or element that is experiencing an increase in oxidation number is the one that's undergoing oxidation. Because the thing undergoing oxidation is giving up electrons to the other substance, we call it a reducing agent because it's making electrons available to the other thing. It is reducing the other thing. Okay, so terminology, really important in electrochemistry. All right, the reduction half reaction. Opposite of everything we just said. This is the process where the substance is going to gain one or more electrons. Okay, how do we know something's undergoing reduction? We have to go in and assign an oxidation number to it. And if we find that that element or substance is decreasing oxidation number, we know it's undergoing reduction. It is gaining electrons. Because this is the substance that is taking the electrons from the other substance, it oxidizes the other substance, and we say that this substance behaves as an oxidizing agent. Okay, all right, so once again in redox chemistry, you just want to be really on your toes with terminology. Okay, so important things that you want to be able to do is look at a reaction and predict, first of all, is this a redox reaction, yes or no? And if it is a redox reaction, is it balanced? Okay, and it's not as easy as you might think. So let's look at this first reaction here. Okay, you've got iron in its 2+ oxidation state reacting with aluminum, yielding iron in its 3+ oxidation state and aluminum metal. Okay, first of all, is this a redox reaction? You don't know. Until you go in and assign oxidation numbers, you do not know that this is a redox reaction. Okay, we're going to learn how to do that in a minute, but the answer to that question is yes, it is a redox reaction. Okay, second question, is it balanced? Okay, from everything we know about balancing, I've got one iron left, one iron right, one aluminum left, one aluminum right. It looks balanced. Okay, truth be told, this reaction is not balanced. Okay, so your eyes can deceive you with redox reactions. You've got to go in and do the hard work of assigning oxidation numbers, determining if it is a redox process, and if so, then you have to go through the balancing process. Okay, next reaction, hydrochloric acid with sodium hydroxide giving sodium chloride and water. We should recognize this. This is definitely acid-base reaction, but is it also a redox reaction? We don't know until we go in and assign oxidation numbers and have definite proof. All right, so the first important thing that we need to learn to do is to balance redox reactions. So, the first thing about a redox reaction is we need to know if it's a redox reaction or not. So to be a redox reaction, we have to have changing oxidation numbers. So the first thing, very fundamental, that we must be able to do is go in, assign oxidation numbers, and if there is a change in oxidation number to our substances, then it is a redox reaction. So we should proceed with the balancing. Okay, so in terms of assigning oxidation numbers, there's a set of rules that you must follow. Okay, and so here's the rules real quick. All right, if you have a pure element, the oxidation number of that element is 0. So if you're looking at O2 gas, that's a pure element. All that's in there is oxygen. So we say the oxidation number of oxygen in that substance is a 0. Okay, monatomic ions, they're easy to identify. So when I look at manganese in its 2+ oxidation state, okay, the oxidation number of manganese is +2. It's simply the charge on that ion. Very simple. Hydrogen. Okay, hydrogen is usually +1 in the vast majority of substances. The only exceptions are if you have hydrogen with a metal. Those are metal hydrides. In that case, hydrogen is a -1. So if you're looking at hydrogen in water, its oxidation number is +1. Okay, if you're looking at hydrogen in a sodium hydride, it's a -1. Okay, let's get rid of some of this stuff, clean up our slide. Okay, moving on. Okay, oxygen. Oxygen is usually -2. If you look at oxygen in the water molecule, oxidation number of oxygen is a -2. Okay, the oxidation number of hydrogen is a +1. Okay, for oxygen, the only exceptions to the -2 is if oxygen is in a compound known as a peroxide, and in those cases, oxygen is -1. So in hydrogen peroxide over here, the hydrogen oxidation number is +1, and the oxygen oxidation number is -1. Okay, our group 7A A elements, the halides. Okay, these elements are typically -1. Remember, if they gain an electron, they have a noble gas configuration, they're happy. So in a compound like carbon tetrachloride, each chlorine is going to have an oxidation number of -1. Okay, I don't know what carbon is. I'm going to put X there for now. Okay, all right, so halides are typically -1. All right, now here's the really important things that we need to know to get the correct oxidation number of elements in all substances. Okay, first of all, if you have a neutral substance, so a compound, more than one element, but it's neutral, okay, when you add up the oxidation number of all the atoms, they have to add to 0. So that's why when I did H2O, okay, we said hydrogen is always +1, oxygen is always -2 unless it's a peroxide. This is not a peroxide. So I have 2 hydrogen at +1 plus my 1 oxygen at -2, and notice that adds to 0. This is a neutral molecule, no charge. So when I add up all the oxidation numbers, they have to add to 0. Okay, polyatomic ions. Oh, what about this one? Cr2O7. That whole thing carries a 2- charge. Okay, the rule is that when you add up the oxidation numbers for each of the elements in the ion, it has to add to the charge on the ion. Okay, so what do we know? We know oxygen is -2. I do not know the charge on the chromium ions or chromium atoms in this polyatomic ion. Okay, I do know that all of this has to add to the charge on the ion, which is a -2. Okay, all right, so starting with what I know, I have 7 oxygen, each at an oxidation number of -2. I have 2 chromium. I do not know the oxidation number, X. I'm trying to figure that out. Okay, so if you treat this just like an algebraic equation, you've got -14 plus 2x has got to equal -2. X is going to equal, you add 14 to both sides, 2x has to equal, let's do this, 2x has got to equal, when you add the 14 to both sides, it's got to equal a +12. X has to equal +6. There's the oxidation number of the chromium in the dichromate ion. Okay, so the oxidation number of the chromium is +6. The oxidation number of the oxygen is -2. So that's how you do polyatomic ions. Okay, so the next step we want to do is to look at a chemical reaction, figure out if it's a redox reaction or not. If it is a redox reaction, we want to balance the redox reaction if it isn't already. Okay, so step 1, let's look at this reaction over here. Okay, we want to figure out, first of all, is this a redox reaction? Question mark. If it is a redox reaction, is it balanced? Okay, if it's not balanced, we want to balance it. Okay, so the only way we can know for sure if something is a redox reaction is to go in and assign oxidation numbers. So we got to go back and follow all the rules that we just learned. Okay, zinc over here. That's a pure element. The oxidation number of zinc is a 0. Next substance, HCl, hydrochloric acid. It's a neutral substance. the oxidation numbers have to add to 0. Hydrogen is usually +1. Chlorine is usually -1. There's one of each in the molecule. They add to 0. Next substance, zinc chloride. That is a neutral substance. Okay, chlorine is usually -1. There are 2 of those in the substance. I do not know the oxidation number on zinc currently, but I know it has to add to 0. The oxidation number on the zinc has got to be +2. Okay, last substance, hydrogen is a pure element. Oxidation number on the hydrogen is 0. Okay, so is this a redox process? Well, let's look at each element. Okay, starting with the zinc. Zinc goes from an oxidation number of 0 to an oxidation number of, back up, to an oxidation number of +2. That is an increase in oxidation number. So that tells me zinc is undergoing oxidation. Zinc is losing electrons. Zinc is behaving as the reducing agent because it is making electrons available to something else and is reducing the other substance. All right, next analysis. What is happening to hydrogen? Hydrogen is going from an oxidation number of +1 to 0. That is a decrease in oxidation number. Therefore, it is undergoing reduction. It is gaining electrons. Okay, because it is taking electrons from the other substance, it is behaving as the oxidizing agent. Okay, and notice that nothing is happening to chlorine. Chlorine goes from a -1 to a -1. No change in oxidation number. Okay, so one thing about redox reactions, when we talk about which substance is undergoing reduction, which one's undergoing oxidation, okay, you go in and you assign the oxidation numbers to individual elements, but then we know which substance is undergoing reduction and oxidation. Okay, so basically the zinc is undergoing oxidation, hydrochloric acid is undergoing reduction. Okay, so we have successfully broken up our overall reaction into the 2 half reactions. So the oxidation involves zinc. It's zinc solid going to zinc chloride. Okay. And keep in mind, that's a strong acid. So we actually have hydrogen ions and chloride ions here. Okay, so we actually have chloride ions on this side as well. All right, the reduction is that involving the hydrogen. So we have hydrogen ions in solution giving H2 gas. Okay, all right. So we've broken up the overall reaction into the oxidation and the reduction half reactions. Okay, and we knew which substance is undergoing oxidation because of an increase in oxidation number for the zinc. And for the reduction, a decrease in oxidation number for the hydrogen. Okay, so that's step one, breaking up the overall reaction into the two half reactions. Now we simply mass balance the elements. Okay, so up here in the oxidation half reaction, I have 1 zinc giving 1 zinc chloride. Okay, in the zinc chloride, there's 2 chlorine, so you need 2 chlorine over here. Okay, so I am now mass balanced in my oxidation half reaction. Down to my reduction. Okay, I have 1 hydrogen giving H2 molecule, so I must come back and put a 2 out in front. So 2 hydrogen gives 2 hydrogen. So I am mass balanced with respect to my half reactions. Next step, charge balance. Okay, all right. So the charges on either side of the reaction have to total the same total charge. Right now, for my oxidation, zinc is neutral, but each chloride ion is -1. So right now, I have a charge of -2 on the left side. Okay. The only way I'm going to get a negative charge on the right side is to add electrons. Okay. And since this is neutral, I know I have to add 2 electrons. So now there's a charge of -2 on the right, -2 on the left. Okay, charge balancing the reduction half reaction. Okay, you're always going to add electrons as reactants. Okay, right now the right side is neutral. Currently on the left side you have 2 positive charges. So the only way you're going to get rid of those 2 positive charges is to add 2 electrons over here. Okay, so, and that makes sense. Look, my oxidation half reaction, I'm giving up 2 electrons. My reduction, I'm taking 2 electrons. Okay, so I am charge balanced. Okay, the next step is to make sure you have the same number of electrons being exchanged in your 2 half reactions. So, in summary, remember we had zinc, metal, gaining reacting with 2 chloride ions to give zinc chloride and 2 electrons, right? That's our half reaction thus far. For the reduction half reaction, we had 2 hydrogen ions, and that's aqueous, AQ. Clean that up a little bit. 2 hydrogen ions gaining 2 electrons, forming H2 gas. Okay, all right. So we just want to inspect our 2 half reactions and make sure we have the same number of electrons exchanged. So I'm giving up 2 electrons and I'm gaining 2 electrons. So in this case, we have the same number of electrons exchanged. In the event you didn't, for instance, if this was a 1 electron exchange up here, what you would do is multiply this entire half reaction by 2. Okay, that's not what happened in this case. We're fortunate we don't have to do much more. Okay, so once you are mass balanced and charge balanced, now we can re-add the 2 half reactions to get the overall redox reaction. So adding the 2 together, zinc solid plus 2 chloride ions. Okay, also on the left I have 2 hydrogen ions and 2 electrons. On the right, I have zinc chloride, 2 electrons, and H2 gas. Okay, all right. And if you've properly balanced your 2 half reactions, the electrons should cancel. So I can subtract the 2 electrons here and here, they go away. Okay, let's get rid of them. All right, and remember that in aqueous solution, that's a strong acid, fully breaks up, you could represent this as 2HCl like that. So zinc solid reacts with 2 moles of HCl to produce zinc chloride in solution and hydrogen gas. There's your balanced redox reaction. Okay, so once again, the only way we knew that was a redox reaction is to go in and assign oxidation numbers. Okay, it's a 2 electron exchange for this reaction. Okay, and we are now balanced. Okay, let's do a little bit more difficult redox reaction balancing wise. So this time we are going to balance this redox reaction in acidic solution. Okay, what that means is there's going to be oxygen introduced into our half reactions, and so we're going to need to balance the oxygen. So we are going to introduce water molecules to balance the oxygen on one side. Once we introduce water molecules, you've introduced hydrogen, so on the other side you're going to balance with hydrogen ions. Okay, so let's balance this redox reaction. Okay, first thing, go in and assign oxidation numbers. Okay, all right, we've got a polyatomic ion, manganese, the permanganate ion with a -1 charge. So we know that the oxygen is -2. We don't know the oxidation number on manganese, but it's got to add to this -1 charge. So oxidation number on manganese plus 4 oxygen is -2 oxidation number, and that's got to add to a -1. You add 8 to both sides. X is +7. So the oxidation number on the manganese is a +7. All right, next substance, nickel. That's a pure substance. It is a 0. Other side, MnO2. That is a neutral substance. Okay, oxygen is -2. I don't know the oxidation number on the manganese. This time, X plus 2 oxygens at -2 has to add to 0. It's a neutral substance. Add 4 to both sides. So manganese oxidation number is actually a +4 over here. Okay, and then we have a monatomic ion of +2 charge, so nickel is +2. Okay, so now we have oxidation numbers. So the next step is to figure out what's being oxidized, what's being reduced. So notice that the manganese is going from a +7 to a +4. That is a decrease in oxidation number. That means manganese is being reduced, and it is acting as the oxidizing agent. Okay, so under the reduction half reaction, I'm going to have MnO7, O4 -1, yielding MnO2. Okay, there's your reduction half reaction. All right, so what else is going on? Nickel. Nickel starts out at 0 and goes to +2. It goes from 0 to +2. That is an increase in oxidation number. Therefore, nickel is losing electrons. It is undergoing oxidation. It is behaving as the reducing agent. It's making electrons available to the manganese. Okay, so our oxidation half reaction is nickel solid going to nickel 2+ in solution. Okay, so we have successfully broken our redox reaction into the 2 half reactions. Step 2, now we mass balance the elements. Okay, and once again, we are in acidic solution, so we're going to use water molecules and hydrogen ions to do our mass balancing. Alrighty, so right now, let's go to my oxidation half reaction and mass balance. I've got 1 nickel giving 1 nickel. I'm balanced. For the reduction half reaction, okay, you're okay with manganese. You got 1 manganese giving 1 manganese. The problem is oxygen. Right now I've got 4 oxygen left and 2 right. So here's where we start using the water and the hydrogen ions. Okay, I have 4 oxygen on the left, so that means I'm going to have 2 water molecules over here to introduce the 2 oxygen that I'm lacking. Now I've introduced hydrogen, and I've introduced a total of 4 hydrogen, so I must add 4 hydrogen ions over here on the right to get the hydrogen balanced. Okay, all right, so let me clean everything up and show you what we have here. We have manganese O2- plus 4 hydrogen ions to give manganese dioxide and 2 waters. Okay, so that's how we successfully use water and hydrogen ions to mass balance in acidic solution. Okay, carrying over our oxidation, nickel solid going to nickel 2+ ions. Okay, and I must charge balance with electrons. It's neutral on the left, so I have to add 2 electrons over here. For the reduction half reaction, remember I have MnO4- plus 4 hydrogen ions, giving MnO2 and 2 waters. Okay, to charge balance for reduction, a reduction is gain of electrons, so electrons are reactants. They go on the left. So the charge on the left has to equal the charge on the right. Currently on the right, everything is neutral. It's 0. So I need to add enough electrons over here to get to neutral. I have a -1 charge and I have 4 positive charges there. So notice I'm going to have to add 3 electrons to get charge balance. Okay, all right, so I have successfully balanced my 2 half reactions with respect to mass and charge. The third step, make sure you've got an equal number of electrons exchanged in the 2 half reactions. Okay, currently my oxidation is a 2 electron exchange. My reduction is a 3 electron exchange. Okay, so I need to multiply through my 2 half reactions so that I get the same number of electrons exchanged. So oftentimes this is what you call the least common multiple, right? So 2 times 3 is 6. So in order to get to 6 electrons, I'm going to have to multiply through by 3 up here and multiply here by 2 to get to 6 electrons. Okay, alrighty, so let's do that and see what we get. Okay, you're going to have 3 nickel solid yielding 3 nickel ions and 6 electrons. That's your oxidation. Your reduction is going to be 2 manganese ion, permanganate ion, plus 8 hydrogen ions in solution, plus 6 electrons, yielding 2 MnO2, 4 waters. Okay, so we are finally ready to add our 2 balanced half reactions to get the overall redox reaction. Okay, once again, if we've done everything correctly, I've got 6 electrons on the right, I've got 6 electrons on the left, they cancel. And so now my overall reaction is going to be 3 nickel solid plus 2 MnO4 minus in solution plus 8 hydrogen ions in solution. It's the left side. Took these guys out. Then I get 3 nickel ions in solution, 2 MnO2, that's a solid, and 4 waters. All right, there is my overall balanced redox reaction. So if you balance in acidic solution, it's just a little bit more work when you get to the mass balance, and you complete that with water molecules and hydrogen ions.